Right, you tens, you are now on part 3. You're on the finishing straight. You've worked well. Part 2 was a lot to take in. In the session, we're going to be focusing on analyzing graphs. And I'm going to give you a few big tips that will help you score maximum marks in any assessment questions. So, with a heading, analyzing graphs, let's get going. Okay, so for our rate of reaction graphs, we either going to have, if we're measuring the mass lost, we're going to have a curve that's going to be sloping downwards, or if we are measuring the product produced, we're going to have a curve that's going upwards because there's more and more product made over the course of the reaction. So in this graph, we've got time on the x-axis, we've got what we're finding out, the dependent variable on the y-axis, the amount of product, and we're going to check what happens over time. Now I've got a little bit of a key there for you, and this is the graph we're going to get. Now we always need to go back to that all-important collision theory. Why does the graph look like this? Well, what are we seeing? We know from the collision theory that at the beginning I've got reactants A and B, the white dots and the yellow dots. And they first got to collide before anything happens. So once they start colliding, once I've added the two reactants together, all the reactants are available to react. And they're going to start colliding with each other, and as they collide with each other, they're going to start producing product. So in the conical flask, if I could see the particles, I would now see a mixture of reactants and products in the conical flask. And then as time goes on, there's going to be less reactants available to collide, and therefore the rate of the reaction is going to slow down. And finally, when the graph flattens out, that's because I've only got products left. There's no more reactants available to collide, or one of the reactants is finished, and therefore there's no more product that can be produced, and I get this lovely flat line. Right, so always go back and think about this in terms of the collision theory and the particles colliding with each other. Now, in the exam, they love to ask these questions where you have to describe and explain rate graphs. Now, there's a difference between describe and explain. If I say to you, cover the screen and describe the graph, you will need to say to me, it's a curve. It starts off very steep, and I know that because the gradient is very steep at the beginning. Then it becomes less steep, so there's less gas being produced, and then eventually the gradient is 0, and that's because the reaction is stopped. There's no more gas being produced. So that is what I'm seeing. So if they say describe this graph, that's exactly what I would say. The curve is steep to start off with, becomes less steep, and then it is flat. Okay, so this is the reaction with magnesium reacting with sulfuric acid, producing magnesium sulfate plus hydrogen, an acid and a metal giving you a salt and hydrogen. And this is the hydrogen gas we're collecting in this upside down burette with water. Now, what about the explain? What if they said, rather than describe the graph, they said explain the graph? Now explain, the moment you hear that in your head, you've got to have a little light bulb going off, going because. Why is it doing that? It's doing that because. So why is the gradient steep at the beginning? And it's steep because there are lots of magnesium and sulfuric acid particles available to react and to collide. Why does it start to decrease with time and the gradient becomes less steep? Well, that's because with time there's less magnesium particles available to collide with the excess sulfuric acid particles successfully, and therefore it slows down. And finally, if I move that out the way, why does the gradient become 0? And that's because at some point there'll be no more magnesium left to react with the sulfuric acid, so there'll be no more hydrogen produced. So that's the maximum amount of hydrogen that will be produced with the amount of magnesium that was added to the sulfuric acid. So stop the video for a moment and make notes in 2 different colors on your graphs. The blue boxes are the explain parts, and the other boxes are the describe boxes. Make sure you can separate the 2 from each other. Well done. Now let's see if we can put this to practice, and you don't need to write this down. I just want you to sit and listen and make sure that you could do this if you were given an exercise like this in class. So on the screen I've got a couple of different scenarios. I've got 3 grams of magnesium ribbon added to a concentration of 1 molar of hydrochloric acid at room temperature. And this is the graph that I have drawn for that situation. So it's 3 grams of magnesium ribbon to 1 molar hydrochloric acid at room temperature. Now, if that's what my first graph looks like, how would you plot this in relation to that? So this card reads 3 grams of magnesium. So I've got the same mass of magnesium is added to 1 molar of hydrochloric acid, so it's the same concentration of hydrochloric acid, but this time the temperature, rather than being at room temperature, it's at 40 degrees Celsius. So can you remember, how does temperature affect the rate of the reaction? You're right. As you increase the temperature, the magnesium and sulfuric acid particles will have more energy to collide with each other successfully more often. So what's going to happen to the rate of the reaction? You're right, it's going to get faster. So how is that going to show on my graph? Absolutely right. The gradient of the graph is going to be steeper. I've still got the same amount, same mass of magnesium, and I assume the same volume of hydrochloric acid. So for this one I'm going to draw a steep curve, but because I've got the same amount of reactants, I'm still going to produce the same mass of, or the same, I should have put centimeters, the mass of hydrogen produced in centimeters cubed. So I'm still going to produce the same volume of hydrogen gas. Now, that sometimes confuses people. If I bake a cake faster, but still use the same amount of ingredients, I'm still going to get the same size cake. I'm not going to suddenly, because I'm doing it faster, get a bigger cake. So all that's happening here, I've still got the same amounts of ingredients, the 3 grams of magnesium and the 1 molar of hydrochloric acid, and let's say I use 250 mils of that. So I'm still going to produce the same final volume, in this case 40 centimeters cubed of my hydrogen gas. Okay, so this is our blue one. I'm going to put our blue one over there for the moment, or I'm just going to, let's just give it a code blue. Okay, then let's look at C. 1 gram of magnesium ribbon. Now straight away there I'm noticing a change, and notice how I always just pick up when I read the question with a highlight or underline, the key parts. 1 gram of magnesium ribbon is added to 1 molar hydrochloric acid at room temperature. So now I have the same concentration, the same temperature as the graph I did in black, but this time I've got 1/3 of the mass of the magnesium. So this time in purple, same temperature, same concentration, so it's going to be the same rate of the reaction, but this time I'm going to produce 1/3 of the volume of hydrogen because I used less magnesium ribbon. So I'm going to do this over there. So this is graph C. And finally, there we go. The last one, if I've got 3 grams of magnesium filings, now what's filings? Filings means it's little particles, so it's powdered. So straight away, I've increased the surface area. 3 grams of magnesium filings added to 1 molar hydrochloric acid at 40 degrees Celsius. So it's going to be very similar to B, except not only does it have a high temperature, so it's going to have a steeper gradient than A, but in addition to the high temperature, it has a greater surface area because smaller parts have a greater surface area to react with. So I'm going to use my pink pen, and same volume, same mass, and same volume of hydrochloric acid, but this time it's going to be steeper. So because it's the same volume, it still goes back to 40, but this time my gradient is a lot steeper. So this is D, and I'm going to put pink there and D in there. So you need to be able to see how your reaction will compare if you change the conditions. So you might just in an experiment use 3 different temperatures and you will get 3 different curves, or 3 different concentrations, again you'll get 3 different curves. And it's very, very important that you can explain that in a graph. Okay, now the last little bit is I'm going to give you a worksheet to do with some practice, and then I will put up the purple pen answers for you to double check, just to help reinforce this. This is a great topic. There's a few key concepts that keep on cropping up all the time, which means there's less to learn, but the more we practice, the better we get.